Now we will talk about Treewidth. So I was told by lots of people that why am I teaching this at all to this school? I mean, it sounds a bit complicated. So then I thought that, okay, I had lots of slides, but I still decided that if it is so difficult, I have to try to do something a bit different and see if I can make it accessible. So if you understand, that's great. If you don't understand also, this is the concept which takes lots and lots of time to get a grasp over. So this is like 2.5, 3 hours of talk. So first 1 hour, I'll just talk from very basic, simple, the structure of these objects. And last 90 minutes, I will talk about how to design algorithms on this object. And there can be a whole course just taught on Treewidth, and still the material would not be enough. But so I'll give you some snapshots of things which is easy, simple to understand, and what leads to different set of questions. And the research on this topic is still happening, and there are different areas where it moves on to. Okay, so what are trees? So they are very simple graph. They just look like this, right? They are acyclic and they're connected. There's nothing more to this. Okay, and why do we love trees? Huh? They're good for nature. Yeah. But you're right. Why structurally we like them? Because they're simple graphs and lots of problems which are hard in general, seeing in last 2 years, last 2-3 days, like vertex cover, de-hitting set, and all these kind of questions, they do become easy or tractable on this class of graph. Okay. So now this is a very natural question, that are trees all alone in the world, or there are brothers, sisters, where we can still pick up these tractability things and move on to. Okay. So this whole next 1 hour is to try to define those brothers and sisters of these trees. And in next 90 minutes, I'll tell you why they are really brothers and sisters of these trees by designing some good algorithms for them. Okay. So that's the whole goal. Okay, so first I need to define what tree likeness means. Okay, so here's my graph, A, B, C, D. Okay, this is not a tree, by the way, because they just cycle, right? And I want to see why this graph is tree-like. So here's one way of defining. So what I'm going to do, for every vertex of this graph, I'm trying to find a home in these trees. Okay, so what is going to be a home? Okay, so suppose for the A, we are going in a red home. For D, green home. C, orange home. B, blue home. And what will be blue home? So you take your pen. Okay, so you're allowed to do the only one thing. You pick up for every vertex. You start at any vertex in this tree. You can go wherever you wish, but along these paths and everything. But the moment you leave your pen, that's end of your home. You understand my point? So you cannot put your hands, remove your hands from this drawing. Okay, so it's like think of this on this tree. For this vertex, I'm drawing a home. Like I can go back, use the same edge, no problem. But once you leave this, you cannot come back. Okay, so what you will get is something of this nature. So this is like a red home. This is like a green home. For D, I have drawn, and so on. So this is what I'm going to call it, a home assignment. So if you notice, because I'm forcing you that you cannot remove your hand, what you're going to trace for every vertex is a subtree. What you're going to trace is a subtree of this particular tree. That's all that you're going to. So what is a home assignment? It's basically an assignment of subtree, of course connected, of T. Is that clear to everybody? You could. Nobody stops you. Well, like just I chose one this way. Like, look at this blue guys, no? They're going both sides, right? So there's nothing. You can choose your favorite subtree of this. But again, it will be connected because you're not allowed to raise your hand. Okay, that's it. So let me define what is a good assignment mean. Okay, so good assignment means that preserves edge relationship. What I mean by they preserve edge relationship? So like, I mean, if I just allow you to draw whatever you like, I mean, you could have just taken for this vertex, drawn the whole tree. For the other vertex, drawn the whole tree. I mean, what's a big deal about it? So first of all, not every assignment will be allowed. And so what I'm going to define what a good assignment means is a good assignment must preserve some edge relationship. What I mean by that edge relationship is that if two vertices are adjacent, right, then their home or their subtree must intersect. Right? You get my point? So what do you think? Is the ever good assignment? Hmm? No. They can intersect. If they intersect at edge, they will also intersect. But I'm also happy if they just intersect at a vertex. That's fine. Yes. Oh, you mean this C and D? C is this. Yeah, that's fine. But look at C and D. There's an edge between C and D. But there's C and D. There is no. I'm only talking about if they intersect. If they are adjacent, they must intersect. I'm not saying anything about if they are not adjacent. I'm not saying if they are not adjacent, they must not intersect. Okay? So let's just be very clear. All I'm asking you that if they are not adjacent and they intersect, I don't care. But if you two are adjacent, their home must intersect. Is that clear? Right? So it's just one way. It's not both way. Right? It's not if and only if. Okay? Okay. So definitely this is not a good assignment. Okay? But this is a good assignment, you check. So I just moved this C and moved here. Now if you notice, this is a good assignment. So for every edge, if you look at the corresponding home, they intersect. It's a good assignment. Okay. So first of all, for our tree likeness definition, I will have a graph, I will have a tree, and I will have this good assignment. Okay. Okay. So this is this is wrong slide. Okay. So now tree likeness for us means the following two things, right? Now I'm trying to abstract out whatever we just talked about. You are given a graph G, a tree T, and there's a function from my vertex set tree of T. That's it, right? So if I have to abstract out this definition, then I've given a graph G, I have a tree T, and I'm just mapping a vertex to a subtree in my tree. Is that okay? Okay, and of course, they have all this good property that if they're adjacent, then their subtrees intersect. But now, we need to quantify the likeness in the above definition. So this is how I'm going to define, but what is likeness in the definition? Like, how do I quantify that this is like 5 like trees or 10 like trees? I want to quantify how close you are. I want to give a number to this so that I can say, hey, if it is 1, you are tree. If it is 2, you are like almost like trees. So I want to quantify that. How am I going to quantify that number? Okay. So what do you think are possible potential definitions? You understood my question, right? So this is a bad slide. Okay, so let me. So here it is. Here it encapsulates everything with an example, and I'm asking, I want to define in a G and a tree and a function. How can I define some measure of size of the biggest home? That's great. That's one particular definition. Okay. Okay. So maximum size of any house. Okay. This is correct. But somehow what happens is that if you have very thin stretch of things, you can just define. So this is like, think of this as you're defining bigness. Okay. What other potential definition could be? So this is one definition. There's absolutely nothing wrong in it. Number of? Okay, that's right. That could be. But generally that is a very bad measure because that is talking about some abstract object. that has no relation with the graph at all. You understand my point? So we want to use, like, home is for the graph. We are trying to understand how graph and these trees intersect. Okay? That's right. Okay, so but like you all go, you're in the road traffic networks. You see road traffic networks. What is the common word you hear? If, oh, let's not follow that road because there's a, why there's a traffic? There's a congestion, right? So that's the right word, congestion. Like, so if I have to define some notion of congestion here, what would be the notion of congestion here? What? How can I say someone is used too many times, right? If some vertex of my tree is used too many, is part of too many homes, the guy is too congested, right? So that's another definition. I'm not saying that is a right definition. I'm just saying this is yet another definition that we could define. And it makes more sense because just now you said, right, congestion, lot of things are passing through, then things becomes much more difficult to move around, right? Human nature. Okay. So I'm the maximum load of any node in the tree. And I'm define the what do I mean by load of a node in a minute. Okay. So there could be several definitions. All the definition can lead to different notions. I'm not trying to talk about those notions. I'm going to talk about one particular notion that we will define in a minute. Okay. So this is what the load will be. So we are given a graph G, a tree T, there's a function. And let's think that every function f of v assigns some tree of v, and we have called it TV. So what is the load of a node? Load of a node in a tree is all those vertices for which T appears in TV. Like if a vertex in my tree appears in the home of 5 people, what is its load? Its load is 5. If this some particular vertex appears in home of 25 vertices of my original graph, its load is 25, right? And what is the load of a tree? So load of a tree is defined by T, and F is maximum of loads of any node in the tree, right? So that's it, right? So load with respect to and a function is very clear. Given F, load of these two objects is well defined. Okay. Okay, you want? Okay, so what is the load of this particular vertex? There's a red tree and a blue tree passing through it. So load is 2. Okay. What is the load of this vertex? If you notice, there's a blue guy, green guy, and a red guy, orange guy. So its load is 3. So load of this, so load of, and what is the load of a tree? Load of a tree is maximum of loads of any node in this tree. So what is the load of this particular tree? 3. Right? Is that clear? Okay. Excellent. So now we are getting to a heart of the computational question. So are we good with this definition? Okay? Okay. So if we are good with the definition, we're done with the tree width. Okay, so what is tree likeness means? I'm going to define. So this is what my definition of tree width of G will be. Okay? So I given a graph G, tree width of G, I'm going to define symbol tree width of G. This is my definition. Okay, I give you a graph G. Okay, use your choice which tree you take, not forcing you. This is why T was not my measure. Okay, you can choose any T you like. Okay, so you fix your tree. You now try to find your homes in a way that load is as small as possible. All right, you try to, because you might think, oh, I take very big tree and every home I make disjoint. That is not going to work, because if 2 people are adjacent, you have to make their home intersect. So think of it like a puzzle, right? It's like a puzzle. I have to draw these pictures, which I think I son, and he will have fun doing it. But if 2 things intersect, your object must intersect. And now, given these 2 constraints, even if I fix a tree and say, hey, now give me this function such that load of any node is as small as possible. So that's the first thing, right? So even fix a tree, and I ask you, there are so many functions. If I ask you to find a function that minimizes the load, something obvious. And now I am telling you, for my graph, I don't care which tree you come up with. You decide your tree, you decide your function, but all I care about is the load is as small as possible. Okay? So it's like, this is why it's like minimum over any tree of your nature. It's like think of this way that adversary has only given you this graph and their adjacency. Rest is in your hand. You can do anything. You can choose your tree. You can choose your function. And of course, you have objective that, okay. So for any graph G, what is the most obvious? What is the most obvious? Make one node, make every vertex map to that guy. What is the load of this node? N. If I have an n vertex graph, load of this node is n. So this is a trivial object that you can make. For any graph, I can always come up with such decomposition where the load of a node is this much, right? So game can start, right? Now, if game can start, then you can try to play around, and we'll play around with these things in a minute. Okay. So this is what tree width of graph means. Okay. Yes. No. Objective is to find a tree and a function which minimizes the load. Okay. And I told you that here is a stupid, trivial such object. My tree is a single vertex, and my function maps every vertex to this node. Let's see, every definition is valid. If two people were adjacent, of course they are adjacent because they are on the same vertex. But what is the load of this vertex? N. Not good. Right? I mean, this is of useful, but still useless, right? We would like it to have as little as possible, as small load as possible, right? That's the whole idea. Okay? So this is our definition of tree decomposition, okay? Which is useful, but algorithmically not helpful, okay? But we will now define, so it's exactly the same thing, but now we'll take this and try to write it in a way, the same definition, in a way that it is easier to algorithmically. And that I'm just going to give you in a minute. And historically, we'll subtract -1 from this. Okay? So the tree width of graph will be maximum load over all this, and for your own fun, you remove -1. And I will tell you why historically, whoever defined this, put -1. Right? So even if your graph had n vertex, tree width is n-1 because load is n, and we artificially remove -1. Why? I told you, historical region. And you will get historical perspective in a minute. Okay? There's a reason to do that way. I mean, even if the person who defined it would not have done this, would not have like made any difference to the world. So if you don't like that -1, remove it for yourself. You call yourself tree width blah, and then it's perfectly fine. They're just +1, doesn't matter at all. Okay. Yeah, so if the graph does not have any edges, what should its tree width? 0, right? Yeah. Or, okay, that's one reason, to capture things and also to capture trees. I want to say trees are tree-like with 1. That's, okay, so we'll get there. We'll get there. We'll make some examples. I'm not in any hurry. We still have 45 minutes. Oh, delta means definition. That's a symbol of definition. Okay, sorry. Nothing. Okay. Yeah, I thought that delta, like people use somewhere like this as a symbol, it means that this is a definition we can take. Nothing. This is like, you don't like it, remove it. I mean, okay. Okay, so now let me define you the tree decomposition the way it is given in textbooks. Okay. And maybe we can spend a few minutes saying that why they're actually same. Now, given this G and T, okay, so now if you think what we did, okay, So now what I'm going to say is slightly inverse of whatever. So now I'm taking this load perspective, and for every vertex, this beta tells me my load comes from these vertices. You understand the point? So this beta function is a function from a vertex set of T to 2 to the power vertex set of G. And how it is defined? So you had this, right? So beta of a vertex in D will be, these are my vertices which are mapped to me. These are the vertices whose home is at me. So that is what is called bag of a tree decomposition. Okay? So what is a bag of the tree decomposition? I am a vertex or a node in a tree, and all those people who are mapped to me is the people I'm responsible for. So my congestion, my load is because of these people. So the people who provide load to a node in the tree is defined with a beta function. So it's like a reverse. Okay? Okay, so this is one property. Second, so this is what, and once you define that way, so given load function, I can define a beta function. Like G and T remains the same, and if I had a load function defined F, I can define beta for every node, all those vertices which has a home. This is it. And now you can show beautifully that this beta satisfies the following 3 beautiful properties. What is that? Every vertex has some home. This is what the first property tells. So if I look at union over all the beta, every vertex is mapped to some vertex. That's all that it says. Okay. Then we said, look, if there's a 2 vertex U and V, right? Then, and they are adjacent, their homes intersect. Okay? It means if I look at that node which intersect, it is that guy is also going to contain this U, also going to contain V, and that is what second property tells you. That for every edge UV in EG, there exists a node T in VT such that UV is a subset of that bag, which basically, so that adjacency relationship that we told. And what is the third one? Okay, what is third one? Third one is the way we constructed. What it is, for every vertex, look at all the bags that he appears, that is subtree. That's all that it says. That is connected. But that's how we defined it, no? How we for every, so third definition is nothing but what is SV is nothing but home of a vertex. Because what I'm writing, all those T, so the V belongs to beta of T. So all those nodes in T for which V contributes to the load, it means it's all the subtree on which you marked. So this is basically whatever I just told you, I have written it in a form so that it is useful algorithmically, nothing more. Okay, so people can just define this directly. Okay, and from here you can go back to the load definition. Given a load definition, you can define this. They both are equivalent definition. Okay, so this is what my next slide will tell you. Okay, I will define what width means in a minute. Okay, so this definition, okay, given what we did previous slide. All good? Okay. So now you tell me, so what will be the width of this decomposition? Width of this decomposition is now very easy, right? We would define what is the load of any vertex, the size of the bag, right? So very simple. Width of T comma beta is maximum of bag size minus 1. That's it. And that is what is called, so load, like load of a vertex is its bag, right? So maximum load is a maximum bag size minus 1 and get done. Okay? So this is literally, it's like identical. But this is very easy. Why I wrote like this? Because this allow us to do dynamic programming algorithm on these objects. Okay? Same. So you can think from a perspective, you can bring some other perspective, and you can use it in the way you wish to use it. Any more further question till we move to the next slide? Yes. Huh? Codomain. Okay. Oh, all subsets of vertex set of G. Or 2 to the power Vg means all subsets of Vg. This is like, okay, this is again a standard notation, I thought, right? Don't people write? So if n is like 1 to n, then 2 to the power n is like all subsets of n, right? This is what, because you can define, because I don't know a priori which subsets are mapped to it, right? So I'm saying, okay, I allow you to take any subsets of my vertex set as this. Oh, I just call it a bag. Oh, why am I calling it bag? Oh, this beta, whatever subset, I'm going to call that as a bag. Why? It's a set. It's just that rather than calling it set, which like, I thought that now people have its own name, it will be nicer to use it appropriately. Okay, so here the question, bag, oh no. Okay, what is bag for? Okay, beta of t is called. So beta of t is bag. And what is 2 to the power Vg? All subsets of vertex set. That's it. Any more questions? Comments? Okay. Okay. So, and then what is the tree width of a graph? Again, correct. Same thing. We can also define tree width of G is minimum over t comma beta width of t comma beta. Right? So you choose your t, you choose your beta function and do this. Okay. So now I have defined tree width in 2 ways. So if I have defined tree width in 2 ways, the next question or exercise is definition 1 and definition 2 are equivalent. And please do it. It's obvious. It's like I have not hidden anything, but it's a good exercise. I told you if I have home definition, how you can go. If I have this definition, how will I go to home definition? Very simple. Last property tells you know what is your home. All those v, for every v, I know there is a subtree which is where it appears and that is connected. That is your home. Now with respect to that, define that everything. So, I mean, it's literally same object. I have just given you both perspective to play with 1 and play with 2. Okay. And now in the next 30 minutes, or whatever it is, I would like to see if you can use this definition on your hand. So be prepared with your pen and paper. And here's an example. This is a path of length n. Okay. This is just a path on n vertex. Give me a tree decomposition for this. As good as you can. Huh? Tree width of this. Okay, someone says 1. I'm not going to accept that. So you have to give me a function, right? You have to tell me t, what is my beta? Or you give me the home function, whatever. Anyway. So let's just stick to this, the second definition which I gave you, just to get you used to. You have to give me t and you have to give me beta, satisfy all the 3 properties. So it might be a useful idea if you can take the snapshot of this, if you have camera, so that you can go back. If you have never seen this definition, it is a mouthful to keep in picture. So maybe take a picture and then so that you can see. That's right. Yeah, perfectly correct. Definition, is it 2 or is it 1? Is it 2 or is it 1? Right? There's also -1, no? Okay, so people are saying, okay, so to define a tree decomposition, I need a tree and a beta. So what is my tree for this path? Path plus 1. Do I really need path plus 1? Okay, so someone tells me that I make a path on, and I'm going to just to differentiate from V1 to Vn, I'm going to call them x1, x2, xn plus 1. Okay. This is my corresponding t. Okay. Now you have to tell me what is beta of xi is. So what Vi? Okay, so my friend is telling me that to take, okay, this is his definition. Okay, first of all, why it is a tree decomposition? Does it satisfy all the 3 properties? Is the union of, so what is the first property? If I look at the union of the bags, this should be at least equal to vertex set of G. Does it hold? Yes, no? Okay. For every edge vi plus 1, is there a bag? Yes. Go to xi, right? Xi is a bag which contains this. That's right. Connectivity. Every vertex vi is mapped to which two vertices? Vi is mapped to xi minus 1 and xi. Of course, they are connected. So it satisfies all the three properties. So this is a valid decomposition. And what is its width? Yes. I equal to n. Why? Okay. Okay. So he's right. My mistake. See, you don't need this. What he says, this, and I is from 1 to n minus 1. Is that what you're saying? Okay. See, all of you people can do this. Check. This will be all fine. Should we do the other example then? Beta on xn or phi? I mean, something. I don't know. You know better. But I'm saying you're getting the hang of this, no? That's all that my purpose was. Okay? I will do the harder ones. Yes. Yeah. Mm. Mhm. So from the definition, I have to define my homes, right? So given the second definition, every vertex appears in some subtree, which was connected. For that particular vertex, this is my home, right? So now if there's a u and v, then I know if there's a u and v are edge. So there is a bag which contains both, no? No. There's nothing called contains. Implies. No, it's not. And look, wait. And I don't want you to discuss that with me. First, you should think about it. I'm here. There's a 90 minutes lecture more. So think about it. Okay? When I give exercise, I mean you to think about it yourself. That's my whole motive. Okay? This is because exercises are meant for you to check what you understood. Okay? So this is on purpose. If you want one point of time, not today, tomorrow also I'm here, I'll do the computation for you. 24 hours, think. Okay, tree on n vertices. Okay, everybody talks about same tree. Okay, so T, beta, here's the T. Okay, so let's call this T star. No, let's call this tree T star, and we need to find T beta. Okay, so now you are telling me, sir, take T equal to T star. And what is my beta? Neighbor plus that vertex makes no sense to me. We are getting good. No, all of you are thinking. If tree are not tree-like, then what is tree-like? Yes. So now if you define whatever you did, suppose T star is rooted at R. And for every vertex, okay, correct, excellent. So what he's saying, for every vertex V of my tree, if V is not equal to root, I map it to V and parent of V. Right? So whom do I map? So I map every vertex V. So I take for the bag containing this corresponds to this and its parent, which is unique. If I root my tree at some vertex R, then for every vertex there's a unique parent. Right? And beta of R is R. R. I want to map to R. So it looks different, no? Is this a valid tree decomposition? Do you? How many of you have understood the construction? Are there people who have not understood the construction? You have not understood the construction. Okay. So very simple. So this is my tree, T star. I think of this tree star as rooted as star. Fix your vertex of your desire and say, root this vertex, root this tree. So that's R. Now, if once I root a vertex, every vertex has a parent. This parent is unique. Okay. So how do I map? So I take my tree for my decomposition, same as T star, and say, okay, so what is a vertex mapped to? What is the beta of that particular node? I say, hey, let's go back to the corresponding T star and map myself to myself and my parent. That's a decomposition. That's end of it. Yes? Root maps to root. Beta of R is R. Yes, it has only one vertex. No issue. It may have no vertex for all that matter. Yes? Huh? But this is just one construction. There's another construction I told you in the beginning, right? For this tree also, I make one vertex and map everybody. Or there are multiple constructions. I am trying to make the one with the minimum congestion. I'm always trying to come up with a decomposition which has as small congestion as possible. That's my goal. Okay. Of course, I'm not proving you why there is no decomposition of width lesser. You will see the advantage later, right? And I'm saying, hey, this is one way of defining an object. You define your object and find its application. There's no fixed definition for anything. People have some application in mind. People see some structure. And as I told you, my definition is I want to use tree likeness. And I'm going to show you why it is tree likeness, algorithmically, structurally, everything. Okay. But now, if you come up with a different notion of tree likeness in your head, of course you will have a different definition. I have some utility in my head, and I want to utilize those utility. I want to say the fact, if a problem is polynomial time solvable on trees, then it is also polynomial time solvable on these kind of objects. So what are those kind of objects? So I define a set of objects where I can export these algorithmic ideas here. So that is the basis of my definition. But if you have something else that you are looking for trees, with respect to that idea, if you try to generalize where those can lead to, may have a definition of objects. There's nothing unique. Yes? I can, so that it becomes tree. I'll show to you what is the disadvantage of that. Okay, so what is the disadvantage of that? Imagine if I give you a graph with 2n edges. Or I gave you a graph with n square edges. How many edges do I need to delete so that it becomes a tree? How many? N square. So this is why it's a bad definition. Okay. So is this example clear to you, this construction? Is it first of all, valid decomposition? Every vertex appears somewhere. Every edge, you have forced them to be part of this thing. And connectivity, as before, every vertex appears in its own bag and where? Yeah, and the parent. when it is in parent. So this is basically every vertex. So every vertex appears there. This particular vertex will appear in the back corresponding to its children and back corresponding to itself. And this is a subtree. So this is a connected piece. Every vertex appears in which, look, for example, what I mean by this, look at fix a vertex, say V1, and its parent is parent of V1, and suppose it has a child V2, V3, V4, and V5. When you make a bag for V2, what it will contain? V2 and V1, right? So here the bag. What will this contain also? V3 and V1, this and this. And finally, where V1 lives? In his own bag when he, so if you look at this is a subtree, right? It's connected. So it's a valid tree decomposition. And what is its width? 2 is the maximum bag size, so it is 1. This is why tree width is defined for -1. That I want tree to have a definition which still, this is like if the tree, this object value is 1, so that I can quantify everything else. So that was one reason why Seymour defined this way. You understood? He wanted whatever this property is, whatever this quantified object is, on tree, it should be 1. It should start from there. So he just subtracted -1. There's nothing more to it. Okay, that's it. So if trees are not trees-like, then what is tree-like? Right? Okay. Okay. What about cycle of length n? Let's see. Up until now, paths and trees had tree width 1. What is its tree width? If our intuition for tree likeness is correct, it should not be 1 at least, right? Because we want only trees to get the value 1. Anything which is not a tree, means it has a cycle, should be, according to our definition, is more complex than trees. And that complexity, that it is more complex graph, complex objects than trees, should be visible by this number, right? So what is this? So everybody did it for the path, no? So let's just look at this. I take this, delete V1. What is this? Path. Okay. All of you know how to make a decomposition for path. You make a decomposition for path. And now what I do, I take V1 and map it to everyone. I go and add V1 here, V1 here, V1 here, V1 here, V1 here. I claim to you it's a valid decomposition. So I first compute decomposition for a path. Then I pick up this vertex and go and put it in every bag, right? Or rather, I look at the beta mapping of this, and in every bag, I also go and add V1, 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 everybody. Is it a valid decomposition? Of course, I took a tree decomposition for path. The vertices of the path appears there. All the edges have been taken. All activity has been taken care. Now, for this vertex V1, I added to every one of those bags. What does it mean? All the edges which were adjacent must have been taken care somewhere, right? Vertex appears because V1 appears everywhere. And why it is connected? Because V1 appears in the whole path. So of course it's connected. Okay. And this is no magic about, this particular way of doing anything. We can just say something more fundamental in a minute. So what is the tree decomposition? What is the tree width of this graph? 3. No. So the bag size is 3. So width is 2. Width is 2. Because path, each bag in the path had size 2. Now I added V1 to every bag. So each bag has become at most 3. So 3 minus 1 is 2. We learned the tree width of any cycle is less than equal to 2. Huh? I didn't get it. Or beta V1 doesn't need to be defined. Or beta V1 is V1 itself. Yeah, doesn't matter. Okay, but what we can take from here? Okay, so what we can say from here? Okay, here the G is a graph. Okay, and X is some vertex set of G, and you consider X and you consider G minus X. Okay, so now we just learned that, hey, another way to make tree decomposition is you make first tree decomposition of G minus X and then add all X to all bag. That's another way of making a tree decomposition, right? So if you find small subset of vertices, if you delete and you have something very simple, then I take that simple and add this to everybody. Okay. So what does it mean? If I can get to my simple graph by deletion of small number of vertices, I'm still close to being simple, which also makes sense, right? So in that sense, I could have also defined edges. If with respect to edges, if you can go, you take the both endpoints of these edges, add it everywhere. Okay. So this also implies, so I can define, I can say, okay, so I can say tree width of G is less than equal to min over X proper subset of VG, tree width of G minus X plus X. Because I have a way to decompose. No, delete any subset of X, find a good decomposition of this, add. So I have given you 2 power n different decomposition for my graph. And tree width is supposed to be minimum, so it can only be smaller than all these which I have created. So there are several ways to create this object. So one object is you delete your set X, compute the tree decomposition of this, and take all these vertices, map it to every bag. That also gives a valid tree decomposition. For example, if X equal to VG, take a tree decomposition for, right? If I take X equal to VG, I delete everything. It's a simple vertex. I add everything. That is a trivial decomposition I'm talking about. So now I'm saying that trivial decomposition, you can make many of them. For every subset of your graph, you can make such trivial decomposition, delete it, find a tree decomposition of the remaining guy, add this to everybody. Okay? Fun. Okay, but here comes the more fun stuff. This is my graph. This 9 vertex is my graph. There's nothing more. And I want to see how smart we can be to make a good, come up with a good decomposition for this. This is it. This is the graph. There's nothing more. I mean, this is not like, unlike up until now, I was making Pn, length n vertex. No, this is a 9 vertex graph. Give me a good tree decomposition for this. Think, this will require pen and paper. There are obvious, of course. Take all the 9 guys in one, done. Can you make it slightly non-trivial by the deletion idea we talked about? Huh? So can you come up with anything better than 9? Yeah, that's okay. That's okay. I should have thought about it. KLM. Of course, I have not used this. Okay, you are right. Excellent. You used my trick on myself. I'm very happy. Now this. Your idea will not work here. Maybe it will work, but that will not give you the best. Yeah. Just to make his life harder, I also have this A0, B0, C0. Now, if I apply his ideas, what he's saying, delete DEF, then you get a cycle, and you make a good decomposition for this, then add DEF to everybody else. That's a very good decomposition of width how much? Roughly 5, 6 or something. Okay. So challenge is make something smaller. And only hint is, If I keep on adding this, it is never going to increase the tree decomposition. Okay, I can close my eyes and I can keep adding this padding. Nothing. Like I'm being, yeah. There is one obvious, simple, like you can see one very beautiful simple that irrespective of the width. Now you will tell why we were not trying to do this home definition, because this is such a thin object that there's a way to define their home in a, if you take too much, it will make, but there is something much simpler happening here. Huh? Mm-hmm. We should do. Yes, we will do. How? Give me a T, give me a beta, otherwise I don't accept anything. Okay, I will give you mine in a minute. So let me give you something slightly non-trivial, and then I will ask you even more non-trivial. Okay, so my graph consists of 1, 2, 3, 4, 5. Let's say 1, 2, 3, 4, 5. So this is my 5 vertex path. Okay, so this is my tree, 5 vertex path. Whom I'm going to map? First vertex, I'm going to map this and this to here. Okay. Next vertex, I'm going to map. This goes here. Oh, sorry. Okay. Next, I map this here as well as, so like this and this is the second one. Maps to second vertex. Maps to the third vertex. Like this and this. Okay. Who maps to the okay. Who maps to the last guy is like, okay, he'll map to this guy and this guy map to this. I actually don't need the last guy. You understood what I did? So I took the first two, mapped it to the first guy, to the second guy, second column and the third column. Okay? Third guy, look, so I'm just, think of this like a sliding window. Move, right? You take this, two window, move one step, move one step, move one step, keep doing it. So irrespective of whatever this width is, whatever this lean object is, I can start from here and slide, 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 slide. So the length of this width does not matter. What is it? First of all, is it a valid decomposition? All the vertex sets are there. Why all the edges are there? All the edges appears between two crossing lines, no? And I have put them together in one bag. So edge. What about connectivity? Every vertex appears in just two consecutive people. So this is connected. And what is the width of this decomposition? Huh? 5. 3, 3, 6, right? 5. Can you come up with the same scheme, but slightly more smarter? Yeah, but like that is just because I have only this much. But imagine that it is infinite. Imagine that this is like 3 cross n grid. Okay, so suppose this is 3 cross n grid. Irrespective of this, still the width is 5. Okay, but I'm saying you can even do better. You can do even smaller. Mm-hmm. Excellent. So what he's saying, and I will not prove this, this is for you to figure it out, it's not some rocket science, is what he's saying, let's be a bit more smarter and let's go like this. One, this, and then move around like this. So try to find out maintaining. So that will have, any bag will contain just, so it's like a hook, like this. Rather than taking both, I take this. So I take care of this. Next, I take care of this. Next, I take care of this. And then I move again like that would have taken everything inside this, right? So that will give you 3. Okay? And there's a magic to show you cannot do 2. Okay? And there's a magic to show you cannot do 2. So, okay, I will do this later. Okay. So you can ask several questions. No? What makes Treewidth big? Okay? So there are several things which makes Treewidth big. Presence of a big click. If a graph has a big click, means set of vertices which are paired with adjacent. Why? You can prove whatever maybe the 3D graph is. You cannot separate this click. They are going to be part of one bag. If that are going to be part of one bag, irrespective, whatever 3D composition you make, a click is going to sit very nicely into some bag. So that already gives you a lower bound, no? But if this was the only obstruction we could have thought of, then sparse graphs of maximum degree 3, there's no click, no? So if they were the only people or only graph which makes Treewidth big, graph should have very small Treewidth, no? Which is not the case. Right? So they are not the object which makes the Treewidth big. There are some else which makes the Treewidth big. So I just now told you, right? Look at this 3 cross stretch. I can show you cannot have any smaller than Treewidth 3. But if I take K cross K grid, I can apply the same idea which we were just talking about. And we can show Treewidth of this K cross K grid is exactly equal to K. This is sparse. In fact, this is a planar graph because I can draw it on the plane without crossing of edges. So it is as simple a structure that we can think of geometrically, we can, but this Treewidth is large. Okay? And this object, not as a subgraph, not as an induced subgraph, but there's some operation called minors. Okay, we'll talk about it if time permits in the next class, are the real obstruction. These are the people who are real obstruction. So what you can show, what I mean by real obstruction, if this object doesn't exist, Treewidth is small in some sense. If Treewidth is big, this object will be sitting somewhere hiding. This is what I mean by obstruction. These are the objects which obstruct the tree decomposition of a graph. Okay, so we started with a very simple definition. We played around, and we'll come back at next lecture and see why these objects are this, and then get to the algorithms. Okay, so that's the plan. And so try to show that Treewidth is at most K for this object in next 1.5 hours or whatever time it is. Okay, thanks.